Welcome to the second lecture of week 3, which is on fluidization. Now if you remember lecture 1 of week 3, there we have defined fluidization, we have discussed minimum fluidization condition, how it achieves that we have discussed. Now in this lecture we will see how to compute minimum fluidization velocity for fluidization process analytically as well as experimentally. So you see, if flow conditions within the bed are streamlined, the relation between fluid velocity uc, pressure drop delta p and voidage E is given for a fixed bed of spherical particle of diameter d by Carman-Kozeny equation. So you see here we are considering streamline motion, streamline movement of fluid. It means we are considering laminar flow, and for that purpose Carman-Kozeny equation is defined for fixed bed. So first we will see this equation for fixed bed, and then we will translate to the fluidized bed. So for fixed bed, the Carman-Kozeny equation is this: UC is equal to 0.0055 E cube 1 minus E whole square, pressure drop, that is delta P, d square by mu L. So pressure drop across the bed, mu is the fluid viscosity, L is the height of bed, d is the particle diameter, and it is specifically proposed for spherical particle. So this is for fixed bed. Now for fluidized bed, the buoyant weight of the particle is counterbalanced by the frictional drag. Now what happens in fluidized bed, if you consider, if you remember the first lecture of week 3, the last slide of that lecture contains the derivation of pressure drop of fluidized bed. So that pressure drop relation we have obtained like this, that is pressure drop equal to L 1 minus E rho S minus rho into G. If you remember, this expression we have derived based on force balance. Now when we put this pressure drop over here, we can have the velocity for fluidized condition. So in that case, UC should be equal to 0.0055 E cube 1 minus E d square rho S minus rho G by mu. So while putting pressure drop for fluidized condition, we can obtain this velocity UC for fluidized bed. Now as we have to define the minimum fluidizing velocity, some other factor we have to consider, because as the upward velocity of flow of fluid through a packed bed of uniform spheres is increased, the point of incipient fluidization is reached. Incipient fluidization, you understand, that is minimum fluidization, and that we have already discussed in the last lecture. So the corresponding value of minimum fluidizing velocity, that is UMF, is then obtained using EMF. If you remember the last slide, there we have defined the voidage of the bed in terms of E. Now velocity corresponding to that is UC. Once we have to define the velocity for minimum fluidization condition, that is UMF, so voidage which is obtained at minimum fluidization condition, that also we have to consider, and that will be represented by EMF. So the same equation but with different terminology, UMF we are considering and EMF we are considering. Value of EMF will be a function of shape, size, distribution and surface properties of the particle. Substituting a value of EMF as 0.4, we can get minimum fluidization velocity is 0.00059, and this expression is put as it is from the previous equation. So you see here, though we have to calculate voidage, but if voidage is equivalent to 0.4, the minimum fluidization velocity we can calculate directly from this expression. So all these expressions are valid till the laminar flow occur, or till the validity of Carman-Kozeny equation will be found. So when the flow regime at the point of minimum fluidization or incipient fluidization is outside the range over which Carman-Kozeny equation is applicable, like if flow is not streamlined, it is necessary to use one of the more general equation for pressure gradient in the bed, such as Ergun's equation. So, when we see the Ergun's equation, it is denoting the pressure drop across the bed, and the whole equation is like this, where d is the diameter of the sphere with the same volume and same area ratio as the particle. So, diameter should be equal to the diameter of a sphere having same volume and same surface area as the particle. Substituting E equal to EMF at minimum fluidization condition and velocity UMF we will put over here. So, and pressure drop condition, pressure drop expression we will consider for pressure drop we have defined for fluidizing condition. All these expression we will put over here. So, this is the expression for Ergun's equation when minimum fluidization condition will be achieved. Now, we will multiply both side of Ergun's equation at minimum fluidization condition by this factor, that is rho d cube by mu square 1 minus EMF. When we multiply this, we are getting equation like this. Now, in this equation, here if you consider this particular expression, this is resembling to or this is equal to Galileo number. Galileo number is defined through these parameters, and similarly if we are considering this factor, this expression, what is this? That is nothing but the Reynolds number at minimum fluidization condition. So, because here we have minimum fluidization velocity, so accordingly Reynolds number would be at minimum fluidization condition. So, what we are doing here is we are converting whole Ergun's equation at minimum fluidization condition in dimensionless form. So, final equation should be GA, that is Galileo number, equal to 150 1 minus EMF by EMF square, that is already dimensionless, and here we have Reynolds number, and this parameter, this factor we have kept as it is, and further this factor will be equal to Reynolds number square at minimum fluidization condition. So, you see it is in terms of dimensionless groups. For typical value of EMF is equal to 0.4, Galileo number should be like this 1406, Reynolds number at minimum fluidization condition plus 27.3 Reynolds number square at minimum fluidization condition. So, this final equation we can obtain at EMF equal to 0.4. Once we solve this, we can get Reynolds number 25.7 and whole expression is shown like this. Similarly, for voidage 0.45, Reynolds number we can find by this, obtained by this equation. Now, once we have the Reynolds number at minimum fluidization condition, that we have already seen how we can get that for streamline flow and for non-streamline flow also. Once we have this Reynolds number value, we can calculate the minimum fluidization velocity through this. So, by this way we can calculate minimum fluidization velocity analytically, but this is specifically used for spherical particles. Now, how we can calculate minimum fluidization velocity experimentally? The minimum fluidizing velocity UMF may be determined experimentally by measuring the pressure drop across a bed for both increasing and decreasing velocity and plotting the results. So, what happens? We can carry out fluidization experiment, and we have to note down the data of pressure drop as well as velocity, and that pressure drop and velocity data we can draw in the graph as shown over here. So, first of all we draw this graph for increasing velocity, and then for decreasing velocity we can observe this nature of the graph. So the two best straight lines are then drawn through an experimental point, and the velocity at which their point of intersection is taken as the minimum fluidizing velocity. So how we can calculate minimum fluidizing velocity is, this is one straight line, this is another straight line. If we join these two lines, this should be the intercept. So that intercept is resembling to minimum fluidizing velocity. So in this way we can calculate minimum fluidization velocity experimentally. So till now we have seen the minimum fluidization velocity expressions for spherical particle only, but in general particle carry different shapes. So how we can consider different shapes of the particle to compute minimum fluidization velocity or minimum fluidizing velocity. For this, Wen and Yu examined the relationship between voidage at minimum fluidizing velocity, that is EMF, and particle shape phi s. Phi s particle shape, when we are considering, we are speaking about sphericity of the particle, which is defined as phi s is equal to d by dp. So this expression is given by Wen and Yu. From this condition we can calculate whatever d we have used earlier, all that d will be replaced with phi s into dp, where d is 6 Vp by Ap and dp is 6 Vp by pi. So here you see this dp is basically diameter of the particle having equal volume as that of the particle, which is nothing but Vp. In practice, the particle size d can be determined only by measuring both volumes like Vp and areas Ap of the particles. So once we know Vp as well as area Ap, then only we can define diameter d, as we can see from this equation. Since this operation involves somewhat tedious experimental technique, because we have to observe two parameter for the characterizing, we have to observe two parameter to characterize the particle, it is more convenient to measure particle volume only and then work in terms of dp and the shape factor. So you see dp is only based on particle volume. So once we calculate the particle volume, we can define the particle diameter. It's not necessary to calculate or to obtain volume as well as area of the particle. The minimum fluidizing velocity is a function of both EMF and phi s, and Yu showed that these two quantities are in practice interrelated. So voidage as well as shape of the particle will be interrelated. Why? How we can say that? Because voidage can be obtained based on shape of the particle itself. Like if particles are a sphere, the uniform voidage we can obtain throughout, but if particle shape are quite irregular, we can have small voidage somewhere and somewhere we have large voidage. So EMF will be directly associated with the shape of the particle. So these authors, like we are speaking about Wen and Yu, have published experimental data of EMF and phi s for a wide range of well characterized particles, and it has been shown that the relation between these two quantities is essentially independent of particle size over wide range. So you see the relation between EMF and psi s, they have proposed two different relations, and these relations are independent of the particle size. The experimental information carried out by the authors are shown over here. They have plotted EMF versus phi s, and they have shown different points, experimental point over here, and when they draw the line of these equations for EMF and phi s, the solid line shows first expression, that is 1 minus EMF by phi s square EMF cube equal to 11, and dotted line shows second expression between shape factor as well as EMF. So once you see the plot of these two lines, you can see that these lines satisfy the experimental data nicely. Now what happens? We have to obtain the minimum fluidizing velocity for irregular particle. So it was the Ergun's equation, if you remember, where pressure drop we have replaced E, we have replaced with EMF, and U we have replaced with UMF. Here D should be replaced with phi s into dP to consider shape of the particle, and along with replacing D with the phi s and dP, along with this we have to multiply both sides with this factor. So here we have replaced D with psi s square into dP square, and similarly D should be replaced as psi s into dP. So here you see D square is replaced with psi s square dP square, and in this expression D is replaced with psi s into dP. Multiplying both sides by this, we can obtain this expression, and then we can replace 1 minus EMF by EMF cube 1 by psi s square equal to 11, as just we have seen these relationship was proposed by Venn and Yu, and similarly this expression we can equate to 14. So after putting these value, and here you understand this is Galileo number, this is Reynolds number at minimum fluidizing condition. So putting all these factors, we can obtain Galileo number for the particle, because this is not of regular shape. We can have 150 into 11, this can be replaced by 11, and here this is replaced by Reynolds number for particle at minimum fluidizing condition, and similarly 1.75 into 14 we can obtain from here, and this is Reynolds number of particle square. So this is the relation of Galileo number and Reynolds number of particle, and once we solve this to get the Reynolds number for different particle shape we can obtain by this equation, that is 33.65, and in bracket we have this expression. So once we have obtained the Reynolds number of particle of different shape, we can calculate minimum fluidizing velocity for different shape particles. Now further we will relate minimum fluidization velocity as well as terminal settling velocity of the particle. You understand what is terminal settling velocity? When particle is moving without having any net force acting on this. So the minimum fluidization, so at terminal settling velocity, particle will move with the fluid. So minimum fluidizing velocity UMF may be expressed in terms of free falling velocity. So here first we should understand what is the difference between minimum fluidizing velocity and terminal settling velocity or terminal falling velocity. Minimum fluidizing velocity is obtained when fluid will start moving with the particle. It will start moving with the particle, and terminal falling velocity is that velocity where particle will be carried by the fluid. So you understand, at minimum fluidizing velocity particle will start moving, it will not be fluidized completely, but at terminal settling velocity particle will be carried out by the liquid, so it will be beyond fluidization condition. So minimum fluidizing velocity UMF may be expressed in terms of free falling velocity U naught of the particle in the fluid. The Ergun's equation related to Galileo number and Reynolds number in terms of voidage for minimum fluidizing condition is this, that just we have seen. This is specifically for a spherical particle, and similarly when we have to correlate the particle Reynolds number at terminal falling velocity with Galileo number, we can obtain this particular relation, that is Reynolds number at terminal falling velocity equal to 2.33 Galileo number 0.018 minus 1.53 Galileo number minus 0.016 13.3. So derivation of this you can find in Richardson and Coulson volume 2. So here we have the graph. This is drawn between ratio Reynolds number at terminal falling velocity and Reynolds number at minimum fluidizing velocity that we have plotted. So you see this graph, it shows the ratio of Reynolds number at terminal settling velocity or terminal falling velocity and Reynolds number at minimum fluidizing velocity against the Galileo number, where EMF we have considered a parameter. So you see how this data we have obtained. For a given Reynolds number, we can calculate a Reynolds number at terminal falling velocity by this expression and Reynolds number at minimum fluidizing velocity using this expression, where EMF we have to put. So for same Galileo number, whatever Reynolds number at minimum fluidizing condition and at terminal falling condition we obtained, the ratio of this we can calculate and we can plot this data over this graph. So you see, different authors have already carried out the experiment, and then this curve satisfy the experimental data, and therefore the ratio of Reynolds number at terminal falling velocity and minimum fluidizing velocity can be related with the Galileo number using these curves. So here you can see, when Galileo number is very small, at that point the ratio of Reynolds number at terminal falling velocity and minimum fluidizing velocity is higher in comparison to Galileo number, in comparison to higher Galileo number. So here we have shown a relationship between Galileo number and Reynolds number at terminal falling velocity for different zones of Galileo number. At EMF equal to 0.4, that is minimum voidage at minimum fluidizing condition 0.4, this relation we can obtain. Now for low value of Reynolds number, that is less than 0.003, low value of Reynolds number at minimum fluidizing condition, that is less than 0.003, and Galileo number less than 3.6. So once we have this, as Reynolds number is very small, this term we can neglect and we can calculate Reynolds number at minimum fluidizing condition using these two terms. So Reynolds number at minimum fluidizing condition is obtained as 0.000712 Galileo number, and similarly Reynolds number at terminal falling condition we can obtain by this, because here Galileo number is less than 3.6. So this condition we can obtain, this expression we can obtain. So ratio of these two will give value 78, which is the ratio of terminal settling velocity and minimum fluidizing velocity, because rest of the parameter becomes equal. Again for higher Reynolds number, that is Reynolds number at minimum fluidizing condition greater than 200 and Galileo number greater than 10⁵. So these are the expression for Reynolds number at two different condition, and the value is 9.1. So you see, at lesser Galileo number higher ratio is obtained, and for higher Galileo number lesser ratio is obtained. Therefore if we see these value, it shows that U naught by UMF is much larger for lower value of Galileo number generally obtained for a small particle than with high values. So for a smaller particle, the ratio of U naught and UMF is larger in comparison to large particle. For particulate fluidization with liquid, the theoretical range of fluidizing velocity is from a minimum of UMF to a maximum of U naught. So you see, for particulate fluidization, the velocity of fluid should be between UMF and U naught, that is lower and upper range of the fluid velocity in particulate fluidization. So here we have to summarize this lecture, and this summary consists of summary of lecture 1 and lecture 2 of week 3, and it goes as: fluidization is defined along with its type, fluidization characteristics are described, minimum fluidization velocity is defined and the effect of shape on it is discussed, and finally relation between minimum fluidization velocity and terminal settling velocity is discussed. Here we have the references, the basic books which I have referred. You can go through these books for further detailing, and that's all for now. Thank you.